I'm Dmitry. I work for Hudson River Trading, which is a company which got its name printed on the backs of your t-shirts. And we're going to talk to them today about how we've been using coroutines for production code for solving production tasks, and what we had to do and what things we had to make them practically useful. So coroutines in C++ are, if you ask me, in kind of a funny state. So as you probably know, they've been added to C++20, which has been 4 years from now. So some sort of a decent support has been added to compilers shortly thereafter. So it's been available for use for a little over 3 years now. I've been to some conferences in the time. I've examined schedules of even more conferences, and it feels like I've yet to see a conference which has less than 3 different talks on coroutines. C++ Now 24 is no exception. Instead of this particular talk, there's going to be 2 more tomorrow at 9 and tomorrow at 11. I also highly encourage you folks to go attend it if you're interested. But despite all this, I talked to a number of engineers. I'm yet to see a person who would stand up and say, yes, we are using coroutines in our production code to solve user tasks. So somehow this feature have so far managed to escape being practically useful. There are a number of factors contributing to that. Among, to name a few, is I'd say lack of established best practices, do's and don'ts, and kind of things, which kind of make people confused about and don't fully understand how to profitably use them to simplify, streamline the code. And also, I'd say more or less lack of sufficiently credible and sufficiently developed coroutine framework, as the coroutines have been shipped as a purely language feature without much of any library support whatsoever. So, yeah. So we have been using coroutines for a little over 2 years now. And yeah, as soon as compilers offering coroutine support have made it to our build systems, we thought to use them to streamline certain our IO-bound applications which were written in a traditional callback style, and therefore suffered from all the problems you could probably expect from a sufficiently complicated, non-trivial callback-based asynchronous control flow. But as soon as we started working on it, we realized some challenges we're going to face. So the first thing, as you might probably expect from a company having a few decades of history, we have accumulated quite a few of existing code, mostly callback-based. And of course, writing everything from the ground up was hardly an option. So in order to have any chance of adoption, we needed to provide a clear story of bidirectional cooperation between coroutine-based and callback-based code. Another thing is, our code features our very own custom-built I/O event loop and I/O multiplexer, merged roughly a decade before Boost.Asio was a thing, and since then fine tailored for very specific tasks. So we value those fine tailors, and again, throwing it out and writing everything in Boost.Asio was also practically infeasible. And another thing is, our engineers exhibit what it calls a healthy dose of skepticism and conservatism. So in order to convince them to even try this shiny new feature, you'd have to demonstrate some real benefit of switching. Well, speaking of benefits, I hopefully won't have to advertise and sell coroutines to this particular audience and talk too much about how using coroutines can lead to much simpler and easier to understand and easier to reason code. And if you stick with callbacks or equivalently features or anything else which decomposes into pieces of traditional regular functions, you cannot use local variables. Therefore, you have to manually establish a context of your asynchronous operation, manually propagate it across the stages, which is non-trivial, boilerplate, toilsome, and also hard to do correctly, and easy to plant certain errors, like the one in this, which I'm gonna keep making every single time I do anything like this. As you can see, you remove the buffer, and then we try to access the pointer. And also, of course, any errors have to be handled explicitly, manually, often different branches of the code, whereas in coroutines you could just simply use a specific language-specific feature tailored exactly for error propagation, namely exceptions. So coroutines may simplify certain things. They may simplify reasoning, they may simplify lifetime management, stuff like this. But this does not necessarily mean that they will simplify things for you. So in order to gain some practical benefit of this, you need some cooperation from the framework you're going to implement and from the structure of your program. Which actually brings us to the next section about what the structured concurrency is, why does it matter, and how it might look in C++ world. So if you look at pretty much any asynchronous framework, chances are high it's going to be built around the same concepts again and again. The first thing you're going to have is have some sort of a class which would represent a unit of background work. It could be a thread, it could be an OS level thread, it could be a green level thread, it could be like a coroutine, pretty much anything. They're going to be like a C++ class. And as people have been talking about RAI for almost like half a century now, I believe, chances are lifetime of such background work will be tied to lifetime of this object. While the scope, the thing continues running. So there's also going to be a join primitive, which is like one of the most fundamental things, which are used to suspend the color until another task completes and then return its result or propagate an exception. And there's often, although not always, but often, a detach primitive, which should dissociate the task from the object that represents it. So the task would run alongside and the rest of the program uninterrupted. And when it's done executing, it simply like just disappears. And turns out this detached tasks turn out to be by far the easiest way to mess with object lifetimes. And following some dangling references, there's simply no way to figure out whether a piece of data passed to a detached task is still in use, or it can be reclaimed or freed, whatever. So this code snippet is simply enough to be obviously wrong, as detached coroutine captures a reference to the buffer allocating a stack of regular function, and therefore is going to go out of scope long before the coroutine even gets any chance of getting executed. Fixing this in practice would actually mean that wrapping any relevant context into lots of shared pointers floating around. And another problem is that a detached task does not offer any exception propagation path. So the implementation, when dealing with unhandled exception raised from a detached task, is basically stuck choosing between dropping it on the floor and crossing the fingers it wasn't too important, which is quite a common error handling strategy, or just like hard aborting the whole process. So this naturally translates to a requirement that any detached task must be enclosed in tri-flash block. But again, if you do catch an exception, chances are high you're not going to have any idea what to do with it, again, short of logging and discarding it. So with all those efforts, with managing context, using all those shared pointers, writing manual error propagation code, the whole overall experience is not going to be that different from a good old traditional callback-based approach. So if you want better reasoning and better handling of those problems, the first solution will quickly come to your minds probably would be, okay, how about we just remove detach and require every task to be joined at some point? Of course, this is a good idea, but the requirement is kind of hard to enforce, as you have to force users to specifically type out join, and you cannot force them to do that. So one thing could probably help you with that is, yes, we have a specific member function called destructor, which is bound to execute near the end of the lifetime of your object. So we can empower it to also join unless it's already joined, which kind of resembles the path from set thread to gthread. But the thing is, even though it does make a step in the right direction with respect to object lifetime handling, it still hardly solves any problem with error propagation. Because the first thing, destructor is not supposed to rethrow exceptions. Of course, you can overrule this for your particular class. Contrary to the popular belief, throwing from a destructor is not undefined behavior. C++ specifically states what would happen if you throw an object destructor. But such things are frowned upon, and you have to account for another exception already being in flight. It's all doable. It's so highly discouraged in the C++ community for a reason. But even if you carry all this out, the more fundamental problem still persists. What if a task destructor is actually never reached? And this is a far more common scenario in the synchronous world that you might probably expect. So consider this code snippet. So this is a piece of code which would, somehow accept and somehow serve in a problem-spamming specific way incoming connections. And also, this is sort of like a supervisor in which you're going to reach out to and report, hey, I'm still alive once every second. So ignore for the moment the fact that it's incapable of handling multiple requests concurrently, and think what would happen if report liveness reads an exception. I mean, yes, sure, we would have captured this exception stored in the promise object and hopefully erased from task destructor. But the problem that this destructor follows an infinite loop, which has as well puts the enrichable in there. So in fact, if report line is an exception, the practically visible behavior would be that such part of the program will simply stop executing without any diagnostics whatsoever. So we just traded exceptions not propagating to exceptions not propagating in finite time, which is, well. So it looks like removing detach was a step in the right direction, but it turns out to be insufficient. So the real root cause of the problem is that this piece of code executes in background. And if anything bad happens to it, you can sit there idly until some other code piece bothers to inquire about its fate. That's assuming it's ever going to happen. So to address this problem, we'll have to remove the very concept of a background execution. And instead establish this one ground rule we're going to adhere to. A task can only run if, when, and as long as it is awaited by another task. So this awaiting task serves in capacity of a caller, regular caller in our good old structured programming approach. So first it's going to resume execution once the awaiting completes. But the more important thing is the reverse property, is that once the caller resumes, it can be sure the callee is done for good, and then resources it may have been borrowed, may be used, are no longer in use and can be reclaimed. And second, this co-await statement is a natural place to erase any exceptions unhandled by the callee. So these two properties naturally hold in the traditional structured programming approach. And with this ground rule and support machinery, we're going to bring them to the concurrent world. Hence the term structured concurrency. There's an excellent article, Notes on Structured Concurrency or Go Statement Considered Harmful, which is going to justify all the things in much, much more detail than I'm going to here for the lack of time. And I highly recommend reading it, yeah?
Can one task await multiple tasks?
Sure, of course, and we're going to cover this in a second. So let's try to sketch an API that would account for what we just discussed. So if we notice, even if we have the task type, we're still going to have something to denote our coroutine functions. Merely having it in scope should not kick off its execution. It should be awaiting on the task, which should kick it off and wait until it completes. So this naive code snippet would probably not work as the author might have expected, for it will start the first task, wait till its completion, and then start the second and also wait. Even a total execution time of 2 seconds. So this raises a natural question, just was asked just a minute ago. How to run multiple things concurrently? Was this the whole point of having a concurrent framework, right? So here we start adding combiners. The function which we might take multiple awaitables and group them into one. So the first combiner that comes quickly into mind is all of, that would start all children in parallel, then wait until they all complete, then collect their return times and return them at step tuple. And if any of those raises an exception, we'll cancel anything still running and then re-raise the exception in the calling context. We'll talk about what cancellation means practically in a second. So once we have this all of, the next thing that comes to mind is any of, which behaves similarly, but it also starts all this children concurrently, but as soon as any one of them completes, it's going to go cancel the others. As was natural for all of to return the step tuple, it's just as natural for any of to return the step variant of the thing that were executed. So any of turns out to be remarkably useful if you need to put some sort of an upper bound a lifetime of an asynchronous operation. The most trivial is attaching a timeout. So let's suppose you have this long-running thing which does any sort of network I/O, and then can afford run arbitrarily long when you hang. And if you need to bound execution lifetime, the traditional approach to this would be to accept the timeout explicitly, and then carefully propagate it further downstream to the lower layers, and also do some careful accounting. For the case you cannot just blindly propagate it, for the semantics of the timeout might change if you already spend some time on some preparation steps or something. There's another nice article on how this explicit approach with passing explicit timeout is a bad idea and leads to API not fit for human consumption. So if you have any of, however, what you can do is you can still design a long-running task to task to run as long as it pleases, but you can short circuit it with a trivial awaitable, simply suspend the color for a specified amount of time, and then any op will take care of the rest. This pretty much solves the problem. So instead of specifying a timeout, you can specify an explicit event. So you can publish a reference to such an event somehow, and then any piece of code you can access to such an event, a reference to an event, can use this trigger method to cancel this operation from the outside. That means you can have your background coroutine doing something and have it still be canceled by the press of UI button or something. Another use case for any of is clean server shutdown. If you write sort of a daemon code, you might want to shut down cleanly on sick term or sick int. And normally you'd have to your server class, if there is any, to somehow subscribe for receiving signals itself, deal with use event loop, using this io.stop, that kind of stuff. But with this approach, you can just design this main serve method run forever until canceled, and then again combine it with the signal receive primitive, which is to suspend the caller until the signal is received. And then again, NEO will take care of cancellation of this serve coroutine. And this has a nice side benefit that if signal received is implemented in a reasonable manner, in terms that if it restores a default signal disposition after assuming, you have this nice side benefit of a subsequent signal doing the hard process shutdown. Haven't written 0 lines of code for that. And of course, one of the probably most important use of NEO is racing. So let's suppose you have this resolve all function, which does asynchronous DNS resolution on a specified DNS server, and you want sort of a resilient DNS resolver on top of that. So whenever you need to resolve a DNS name, you start resolving things on Google, and if it experiences any sort of network outage and does not respond within 100 milliseconds, you spawn a concurrent resolution, this time on Cloudflare, and return whichever completes first. So if we draw all those awaitables in a graph and mark which awaits on which, we can quickly notice that those things form a sort of a call tree. It's very similar to a regular called stack, but now all of and any of are branching points for they allow things to run concurrently. So the call stack actually expands into a sort of a call tree. So every node in the tree has another node suspending and waiting for its completion. So this gives out the natural path for exception propagation. And likewise, cancellation naturally propagates down the tree. Once we need to cancel a node, we recursively cancel all the children, then confirm the cancellation to parent. So it looks like all those properties we wanted to achieve naturally hold so far, which is kind of a good thing. So let's give our API a shot and write hello world of concurrent programming, a simple TCP echo server. Well, it could be naturally split into two parts, serve and listen. So it would take an established TCP connection, read bytes and echo them back, and listen would accept incoming connections and spawn serve coroutines as necessary. So serve is boring and uninteresting, so you have your array, you have your infinite loop, your asynchronously read any available bytes and echo them back, and as we use in Boost.Asio for the sake of this particular illustration, which reports any errors as exceptions, but catch exceptions and exit. Not much of anything to discuss here. Listen is a little bit more interesting though. We're also going to have an infinite loop. We're going to asynchronously accept a connection. And what are we going to do with it next? What we need here is somehow run serve concurrently with the next iteration of our loop here. And so far we don't have any means of doing so. Well, one option would be to take the statement literally and rewrite this thing instead of a loop in a recursive way. But come on, really. The ergonomics and the performance would just be questionable at the very best. So but this would work for some definition of work. And if we draw the task tree of this thing, it would look like this. So we have long chain of listens interleaved with all-offs. So task tree actually degenerates into a list holding lots of dead serve coroutines, some of them alive, without any opportunity to clean them up. So it would be nice if instead of all this stuff, we could just have one dynamic all-of, which could adopt more serves as they come and dispose of existing coroutines as they complete. So okay, let's accommodate for that and add this dynamic all-of to our design. But how do that actually look like? So the first thing that might come into mind is something like this. But this violates our ground rule, or as soon as we call this add function, it should probably somehow start running, but there isn't anything suspended and waiting for its execution. So what we should do instead here is to resemble the sketch of the task tree withdrawn more closely. So listen with suspended on a dynamic allow thing. And this dynamic allow would accept the first task as its first child, but then it will be given a handle, which then can be used to spawn more tasks into this dynamic allow. So if we draw the resulting task tree, we can find out it almost perfectly matches normal C++ nesting rule. So we have our listen, which is suspended on dynamic allow, which is suspended on the lambda, which is suspended on async accept. Well, so far so good. This approach gives us an interesting thing though. We now have a node in our task tree which is bound to a variable. In this particular case, this task reference to the lambda. So now we have a variable of a sort of a type. What we can start to do, we can start adding functions there. We already have add, but we can have more. We can have size, maybe we can have cancel. And once this thing arrives, we can quickly figure out that this outdrawn is little simple L of. So it's now something more than that. So what we have just designed is a fundamental primitive of structured concurrency. It appears in pretty much any other implementation which has the word structured concurrency anywhere in its description, and always under a different name. So Python 3, which more or less pioneered the approach, calls them nurseries. Recent addition to Python async calls them task groups. Rust since recently has task scopes. Kotlin, which invented the whole thing independently, has coroutine scopes. But the idea is the same. It is a sort of a scope in which you can submit your tasks. They can run concurrently with the spawner, but we guarantee that they will all exit before we leave the scope. So for the lack of universally agreed upon name, and as our HRT engineers are more familiar with Trio than anything else, we also adopted the nursery name, from the one place where children are. So it's all good, it all works, with one drawback, which is purely like styling. So it requires quite a lot of typing to open nursery block. But we can creatively abuse some operator overloading in C++ macros in order to reduce the syntax to something like this. So now our invariants hold, our properties we were seeking hold, and the overall ergonomics is kind of acceptable. So this piece of code concludes our echo server exercise. One important thing with nursery is that it lacks public constructor. So the only thing to obtain a reference to a nursery is use this with nursery macro, which features a co-await under the hood, and therefore can only be opened in an asynchronous context. So you need to be in a coroutine scope in a coroutine context in order to open the nursery. Nurseries and combiners look pretty much similarly in a sense. So they all act as node in task tree. So they have to wait until all the children complete. If any child raises an exception, such exception would be propagated back to the parent, but not before any children still running will get canceled and confirm their cancellation. So all in all, we have a guarantee that no task is ever left behind to run unsupervised. So far we put some effort into making sure that if we have spawned a child task, it will complete before the parent. But the natural question that arises is, okay, but what if I do need to spawn something with outlive me? Something more or less equivalent is, what if you need to spawn a task from outside the coroutine context? Well, while you cannot break the rules, you can bend them to a degree. And in the sense that if you open a nursery, you can then pass the reference to the nursery into third parties, and as long as the nursery remains in scope, remains open, anybody having reference to there can use it to submit tasks there too. So this listen thing may have been written as this. So there's not much benefit to this, but this would work. So you can see that begin listen is now a regular function and accepts nursery explicitly, and it uses it to spawn things as necessary. So while this does allow us to circumvent the rules, this still happens in kind of a controlled way. So the first and most important thing is every task still has a caller. in a sense that the caller is the thing we are going to return the control to. Is the case the coroutine which opened the nursery block. It is going to deal with any unhandled exception the spawner may have, the spawn task may raise. And of course, this thing does open up for possibilities of dangling references and user free errors. But the thing is, as like any local variable passed by reference to a spawned task is probably going to get destroyed before the spawner, when the spawner exits. So yeah, user free is still an option. But the thing is, passing nurseries explicitly looks like a sufficiently advanced technique. So it would attract some additional attention, some additional scrutiny from both code authors and code reviewers. The next thing is the task cannot run uncontrolled, unlike the test task. Its lifetime is still bounded by the lifetime of the nursery the task has been spawned into. And last thing, the function behavior with respect to spawning tasks can be deduced from the signature. A regular function cannot spawn any coroutines. It lacks any means of doing so. A coroutine function can spawn children, but it's bound to join them before it returns. And if a function, either regular or coroutine, accepts a nursery explicitly, it can use it and likely will use it to spawn coroutines that might outlive it. So while passing nurseries around free function is, from our own experience, an extremely rarely used technique, I cannot remember of any single occurrence of this in our code base. It becomes much more common within the boundaries of a class. So let us suppose, for the sake of argument, that we somehow, for some reason, dissatisfied with systemd and have embarked on making a replacement. So we have our run process coroutine, which does everything required to run something, like prepare the environment, fork off the process, wait until completion, capture log its output, log relevant events, restart if necessary, and so on and so forth. Then we have our start function, which is regular, not even a coroutine, which needs to start the process, and then return and allow the process to run further. As we just discussed, the easiest way to do so is to have a nursery, and then use this nursery to start run process into there. But the question that naturally arises is, where to get a nursery from? Like we already mentioned, nursery can only be obtained from a synchronous context, and C++ objects lack asynchronous constructors, and more importantly, asynchronous destructors, so this is not an option. So the first thing that comes into mind again is, okay, if we need a nursery to function, how about we just accept them in the class constructor? This might look like a good idea on the first glance, but it does lead to certain problems with crisscross object lifetime. Let's consider this code snippet which we're trying to put this thing into use. So we open nursery, then we construct the supervisor, we'll work with it somehow, and then we'll leave the scope. And at this point, supervisor goes out of scope and gets destroyed, but any tasks spawned into the nursery will continue running, and if any of them happened to be member functions, which captured this by reference, now we have reference a dead object which let out of scope. So what we can do instead is establish nurseries ourselves. So instead of accepting it explicitly, we instead have to advertise an asynchronous function run. We should open a nursery, save the pointer to the nursery, and then suspend forever. So now we have established a scope for running our run process things, which are bound to the lifetime of the run coroutine. How we can use it? Well, we create the supervisor class, and then we combine its run and another asynchronous lambda, which actually works with this thing through any of. So a little bit toilsome, but for the lack of C++ equivalent, C++ asynchronous destructor or equivalent of Python's async with, this is the best we have. So, okay, now we're gonna talk a little bit about how actually to implement those leaf awaitables. So we've been so far talking about like tasks, combiners, but how we actually implement with a thing which would wait in something, like the sleep for thing. So as you probably already know, in order to be able to co-await an object of a class, the class must implement three functions. The first is await suspend, which should initiate the asynchronous operation. It accepts a pointer size and trivially copyable coroutine handle, and should arrange its resume method to get called whenever the operation completes. Then we have the await resume function, which is used to fetch the result of the asynchronous operation, or it's allowed to erase an exception if the operation completed unsuccessfully. And we have await ready, which is pure performance optimization, and would allow the runtime to bypass costly await suspend if the asynchronous operation managed to already complete by the time it was going to suspend on, and proceed straight to fetching the result. So this is the composition. Start the operation, notify me when it completes, and then hand back the result. Turn out to be quite versatile in practice, and it allows expressing pretty much any asynchronous operation accepting a completion callback as a C++ awaitable. So let's consider this example. This is a snippet from C_Ares library, which can do asynchronous DNS resolution. So here we have an initiation function, Ares get either info, which accepts the name to be resolved, some uninteresting stuff, and the callback, and the peg pointer to be passed back into the callback along with the result of the resolution. So how can we wrap this into an awaitable? Well, the first thing we're going to need is to provide some space for storing copies of arguments to the initiation function and the result. Then we're going to have our await suspend, which is going to stash the coroutine handle and then call the initiation function, pass it the parameter, pass it reference to this as the peg pointer, and cast it back, and then copy the results back into the object, and then resume the parent. And await resume is pretty much trivial. If we succeeded, we return the result. Otherwise, we throw an exception. So again, this approach turns out to be like versatile and practically useful, and pretty much anything which accepts a continuation callback can be trivially wrapped into an awaitable, whose await suspend just calls begin thing, passes the continuation handle. So with this, now we're going to talk about the most non-trivial part, which is a task cancellation. We already said that our branching node allow any of nurseries can cancel their children in certain circumstances. And now let's talk about what this means in practice, how is this implemented. So as you might have guessed from advertised use of any of, cancellation is extremely important and also extremely commonly used operation in the asynchronous world. But in order to be practically useful, it must have certain properties. So the first thing it should be built in and implicit. Just like C++ exceptions eliminate the need to accompany every function call with this infamous if failed return faith in, a concurrency framework should eliminate the need to write if cancelled return scattered throughout the code. It should just happen automatically. The next thing should be fast, which in practice means no C++ exception should be involved in implementing this. Exceptions are routinely used in other languages and other framework to implement cancellations, where they're cheaper, relatively cheaper to throw in to raise in cache. C++ exceptions are fast unless you actually throw them, and as we have coroutines which are bound to get cancelled every time they invoked, using them for cancellation provides much bigger overhead we're happy with. And perhaps most importantly, cancellation should be asynchronous. In a way, the cancellation may be requested and then completed later, and the framework must be able to deal with it. The asynchronous nature of cancellation is often overlooked, and I'd like to emphasize on its importance. So some of asynchronous operations could be what we call them synchronously cancelable, in a way that at any point you can tell it, please cease to exist from now on, and it will comply. Some of those could have been made cancelable, but wrapping some sort of externally given API which simply lacks any ability to express this thing. So if you're wrapping a sort of C API, chances are high it's going to be phrased something like this, where there's any sort of handle to an in-progress operation inside, but can be captured and then handed back to request the cancellation of this thing. Well, you can't probably treat this as an implementation defect and open. This shouldn't happen, wait for it to get addressed. But more important is some of those operations inherently cannot be canceled synchronously. One of the most trivial example is the running subprocess. Well, what you can do is you can't kill it, but it still have to wait until the kernel processes your signal, delivers it, flushes its output buffer, which can take considerable time if any sort of like network mounts were used, or if the process was already dying and the kernel was busy writing 10 GB long core dump file, which also happens. And only then the process exits and its exit status is delivered to the parent. And if you were to wrap a running process into a C++ awaitable, you have to account for that. And you cannot afford to disregard this and leave dying process behind. Imagine you have this code snippet which should run a process in true environment. We would prepare the environment that would do some sort of bind mount and we'll run the process in there. And the process may be using those bind mounts. And if you get canceled, you need to wait until the process fully completes before you can proceed and mount those things. If you just disregard this thing, you cannot reliably implement a cleanup. So you're going to have like a cascading failures on cleaning things up or just accumulating garbage. Another example is asynchronous I/O, which like appears as IO ring in Linux recent versions, or overlapped IO in Windows have been there for God knows how long. So I'll talk about it later as it's easier to fit in one slide. So here you have your read file X, which accepts an open file, a buffer, a pointer overlap structure, which serves as an identifier for the operation, among other things, and pointer to the completion callback. And yes, you have this cancel IOX function, which could be used to request the kernel cancellation of your read. But even then, cancellation would happen asynchronously. You'll have to wait until the kernel processes this, and would still call your callback shortly thereafter, but still later, and delivered status canceled, or a normal result of the operation if you cancel it too late to manage to complete nevertheless. And before that, the overlap structure in the buffer should be considered in use by the kernel. And if you disregard that and just like free or reclaim it, well, you have your textbook use after free, with the exception that it's going to be the kernel will be messing with your memory, so it's much more hard to detect with any sort of mem checker or whatever. So of course you can't disregard this thing and think, hey, we're not going to support this. But yes, in this case, you are ever opting out from ever supporting anything like this. And when you later discover that you actually need those things, you're going to have quite hard and entertaining time retrofitting asynchronous cancellation into an already existing framework. Rust folks learned this the hard way. They originally, as far as I know, they originally considered all those asynchronous stuff synchronously cancelable, just drop them on the floor at any point. And then they suffered hard enough to actually later consider. Now, I don't keep close track of this, so I don't know if they actually retrofitted this thing to make things asynchronously cancelable. But even I were aware of those problems, even if I don't keep close track of those. So, with all those requirements in mind, how our cancellation procedure could actually look like. So, in the last step is pretty much obvious, as stat coroutine handle, in addition to resume function, gets us destroy, which can be used to just destroy the coroutine frame, along with the promise, all variables, all parameters in scope, and just clean things up. So the cancellation procedure should roughly be laid out as follows. And as always with plans like this, the most interesting part is missing phase 2. Well, as we're seeking to support asynchronous cancellation, we're going to have to request certain cooperation from awaitable. So we should be available to tell the awaitable we want to cancel this thing, the file operation it represents, and provide it a way to notify us later when the cancellation is carried out. Therefore, we have not much of any choice but to extend the awaitable interface even further with some new functions. So the first thing we are going to add is this await cancel thing, which is going to be called when we want to cancel something already in flight. And when the cancellation is carried out, it should notify us about having done so by resuming the coroutine handle we passed to it. And we chose to pass exactly the same coroutine handle we passed earlier to await suspend. So this dummy-looking cancellation, some dummy-looking wait cancel, which simply ignores the argument and does nothing, doesn't even bother to do any sort of cancellation, instead allows the operation to complete naturally, is a perfectly legit implementation. So with the addition of this new await cancel thing, our cancellation procedure would be roughly as follows. When cancellation is requested, we're going to mark our coroutine as having pending cancellation. Then we call await cancel of the awaitable we are suspended on. And then later, some time passes, cancellation is carried out. Let me check if the cancellation was requested, and then we destroy the coroutine or we resume normally. And every half of this cunning plan has its own set of problems we have to deal with. So for one thing, in order to actually be able to call await cancel, we need to keep track of the awaitable object we have been suspended on and its type. And C++ does not get us much of any advantage with that, any assistance with that. In order to solve this, we might take advantage of Promise's await transform function, which can be used, as you probably know, to do some sort of a transformation of an awaitable. So when you co-await a thing, this thing actually is passed through this await transform function, and other await underscore methods are called in the result of that transformation. So how are we going to use this? So we're going to have a class promise. Again, I assume you probably know the basics of the C++ coroutines. So I'm going to cover in deeper details what the promise is and how you probably normally implement it. So we have we'll only be considering cancellation related stuff. So in class promise, we'll have to provide some space for the pointer to the awaitable we're going to be suspended on, and its cancel function. As we're going to have our await transform, we simply wrap the awaitable into class interceptor we're going to implement. The await suspend function of this interceptor is going to delegate to the wrap awaitee, but not before we stash a type race reference to the awaitee and its cancel function. Now, await resume simply, again, cleans up and delegates the awaitee, so that's await ready. So with this thing, we have our tracking in place, and the only thing we have to do now is to actually employ this and call this cancel await cancel the awaitee we suspended on. So now, yes, we have requested the cancellation. Time passes, the cancellation completes. We need to destroy the coroutine. The second problem is that coroutine can only be destroyed as long as it's suspended. But once we resumed, we're no longer suspended. In this undefined behavior to call coroutine handle destroy on a coroutine which is currently on CPU. So we're going to actually wait until its next call wait when we can actually go ahead and destroy it. So what we need here, we need a way for an awaitable to notify us about its completion or successful cancellation without actually putting the coroutine back on CPU. Could have achieved something like this if we passed not a type erased coroutine handle, so an awaitable could actually fetch the promise type and call methods on it, but we have chosen to stick to type erased coroutine handles, so coroutine handle of void, so awaitables could just interact with our asynchronous framework without any knowledge of our promise type and its interiors and the queries of its behavior. So it would be nice if we could pass it a coroutine handle, it could resume, but such resumption, instead of putting coroutine on CPU, would instead invoke a function we're choosing. And it turns out to be possible, but in order to do this, we need to dig deeper into the implementation of those things. As you likely know, when a coroutine function is invoked, the runtime allocates a frame on a heap and puts some amount of stuff in there, which are the resume index, which is basically the number co-wait statement is going to resume at, then the promise object, then all the arguments to the function, all the local variables which are in scope, all the temporary objects whose lifetime still spans across suspension points, and other compiler and runtime-specific bookkeeping. And of course, this layout of such a frame is not standardized, it's compiler-specific and runtime-specific, but compiler vendors took some effort into making sure that coroutines compiled by different compilers can interact and suspend on each other. So you can link together objects built by GCC, Clang, and Visual C, and they all can interact and get suspended on coroutines compiled by different compilers. And in order to do this, all major compiler vendors agreed on the first two members of a coroutine frame. And those are resume function and destroy function, which accept the pointer to this coroutine frame thing. And basically, coroutine handle colon resume can be trivially written down as this. So basically, get the address of the coroutine handle, reinterpret cast it to a frame, and call it resume function. That's it. That's how coroutine handle colon resume works. And equipped with this knowledge, we can now put up a fake coroutine handle and stuff whatever function we want in its resume function. And now we can amend our promise function, promise object, and equip it with this fake coroutine frame in addition to a real one. So it will provide us two handles: a real handle, which when resumed will put the coroutine back on CPU, and a proxy handle, whose resumption will simply invoke a function on resume we're going to write in a moment. And in order to achieve this behavior, the only thing we need to do is to install this trivial trampoline in our fake coroutine frame. So now, having done this, the only thing left to do for us is to modify our interceptor class so its await suspend would not pass coroutine handle was given, which was a real handle, must instead pass the proxy handle to the awaitable. So when the awaitable is done and resumes us, we are going up in our resume function, but the coroutine is still technically suspended. So if we want to, we can go ahead and destroy it. So this completes our asynchronous cancellation thing. Another thing is, as we already discussed, since the cancellation is asynchronous, an operation may manage to complete naturally despite the requested cancellation and produce a meaningful output. And in some cases, such output cannot be simply dropped onto the floor. So imagine you have this async open, for example, and upon completion, it would provide a regular file descriptor. So if it completes, we cannot manage to drop it on the floor. We're going to have a resource leak. So the awaitable, therefore, needs an option to request resumption of the coroutine, even though it's marked for cancellation. And we're going to achieve this by expanding the interface even further. So instead of those 4 functions, we're going to have a 5th one, await must resume thing, which can only be cancelled on a coroutine which has been await suspended, then await cancelled, and the cancellation completed and the coroutine has been resumed. And we're going to inquire whether the awaitable requires us to resume normally and consume the result of the operation, or it can be allowed to get destroyed naturally. So with this thing, a few things might be noticed when implementing the awaitable. The first thing is it has multiple functions which naturally groups into pairs. So with destructor and constructor and destructor, and we have await suspend and await cancel. And one function in each pair reverses the effect of the other. In particular, it would mean the framework will not call await cancel an awaitable whose await suspend has never been called. So keeping this in mind, ideally, an awaitable object should like dormant until its await suspend has been called. Especially, this is especially important if the awaitable is not synchronously cancelable. But if that's feasible, then you might need to account for the situation where the operation is completed before we await suspended on it, or even if the created awaitable object wants to get destroyed without even suspending. So now a few words on the next non-trivial thing, is how to manage lifetime of objects and how to ensure proper resource cleanup in asynchronous functions. So, as I've said, AI has been there with us for almost 40 years now, I believe, but now it's even more important than it was before. So consider this obviously wrong code snippet, and this closed and happy path might have immediately and rightfully caught your attention, as you know that if anything before raises an exception, close will not be called, and we have our resource leak. Until now, though, you could have gotten away with this by enclosing the whole thing in try block, having matching catch, and duplicating the cleanup behavior in catch block. Well, despite looking ugly and obviously violating DRY, that might have worked until now, as any function try block would either complete normally or raise an exception, and we seem to have accounted for either case. But now, the cancellation we implemented opens up with the third option, might just get cancelled without any exceptions involved whatsoever, and in this case, we're going to skip close in both branches and have our resource leak back. So what we need to do is, of course, employ our AI. So in this case, you could use a scope guard offered by like GSL or Folly, or I believe Upsale also has one. So as destruction of a coroutine involves destruction of any local object, it will trigger the destructor, it will trigger the scope guard, and now we have the close being called regardless of how coroutine ceases to execute. Of course, it would be even better simply use a standard file stream whose destructor does the right thing without having to deal with the scope guard and everything. The less trivial question is what to do if the cleanup function is itself asynchronous. So let's suppose we have this async file interface, which might in fact make sense if we're dealing with network mounts, where opening a file might take some considerable time, and we want to work with it. So we already talked about drawbacks of having cleanup in the happy path. But the problem is here, if we try to utilize a scope guard, it won't work either, because the starters cannot be asynchronous, and therefore you cannot co-await in a scope guard. So neither way works. Somehow we need to account for this. So to help with this, we added yet another awaitable adapter until cancelled and, which takes an awaitable, sits there idly, does not kick it off when await suspended, and wait until cancelled, and then it initiates the operation, and wait until it completes, and then it confirms the cancellation. So when combined with any of, then in any case, whether lambda completes normally, or if it raises an exception, or if the whole thing is cancelled from the outside, the second argument of any of is going to get cancelled anyway, and this will trigger the cleanup. And the cleanup can be done asynchronously, and once it's done asynchronously, then the cancellation is confirmed, and we resume the parent or propagate the cancellation. So this pair, until cancelled and paired with any of, is for a degree an asynchronous equivalent of RAI and could be used and probably should be used if you need any source of resource cleanup, which cannot be done through a regular C++ destructor. So there's yet another subtle problem with the implementation we have sketched so far. So to illustrate this, let's write the most trivial synchronization primitive, which could be a level-based event which only allow for a one-way transition from a non-triggered to a triggered state, and plus an option to suspend a coroutine until such a transition happens. The implementation is going to be boring and interesting, so we have a bool for a state, we have a list of awaitables, the awaitable keeps a back reference to the event, it's await ready when the event has already triggered, now we have when suspend, which memorizes the handle in the list, now we have memorizes the handle and sets the awaitable into the list, now we have wait cancel, which erases the awaitable from the list, now we have wait resume, which is dummy, doesn't do anything, we have master resume, which also doesn't do anything, now we have operator call wait, so you can await on the event directly, and you have your trigger, which marks the event as triggered, and it erases our awaitables and resumes them. Not too much of anything interesting to discuss here. Let's give it a shot and try to use it. So here we have two concurrently executing coroutines. One will be waiting on the event, and one would be setting the event. And if we run this thing, chances are we're going to get something like this. And here's where we have a problem. This piece of code looks like a regular C++ function that doesn't have any co-awaits in here, which might somehow justify it or indicate a possible point of a context switch. Yet somehow something squeezed in the middle of it. So we have an implicit context switch in the middle of a regular C++ function. This kind of hinders our ability to reason about the code. Like, after all, one of the biggest selling points of a cooperative concurrency framework is that you normally have some control over its context switching points. And these implicit context switches may indeed lead to bugs which can be hard to discover. Let's rewrite our example a little bit. So it would, instead of simply writing a thing, it would mess with the pointer to something. And then let's actually go ahead and extract those three lines into a totally separate function. Now a function is going to call something totally unrelated, not knowing that even if it's not given any pointer, it still might arrange it to get zeroed out. So despite we have the assertion of the pointer path being non-null, we'll still have a null pointer to reference. And what's worse here, that every piece of code, when looked at in isolation, looks totally legit. There's nothing obviously wrong here. Yet when combined, they lead to some the odd behavior. So it looks like we need another ground rule which would streamline the scenario we just discussed. So each coroutine handle should run each coroutine should run uninterrupted between its co-await and the next co-await. So how could we actually implement such behavior? Well, we do not want to impose any additional requirements on the implementation of the awaitables. We still want to be able just to resume past handles when they want. So what we need to do is we need to alter our promise object. So here we have our onResume function, which we have already written a dozen slides ago. And it feels like what we actually need is one of those executors things, which certain asynchronous frameworks provide as a concept. So we have access to anything like this. We might simply defer resumption of the real handle through the executor until the coroutine hits its next suspension point, and it'll solve our problems. However, we aim to be agnostic of the I/O framework used, and some of the I/O framework, including our own house build, does not provide any concept of executor, and does not have any opportunity to implement it with reasonable overhead. So as we aim to support those cases as well, we are going to go ahead and implement it from scratch. Luckily, we don't need anything even remotely non-trivial from it. No multi-thread synchronization, no nothing. So the only thing we needed from such an executor would be a queue of ready coroutine handle as this runtime function. We should push the coroutine handle to the queue and then drive the queue to completion unless we're already in another invocation of run soon, in which case we just know that outer invocation will take care of executing this thing. With this thing, when we resume the coroutine handle from the coroutine context, such resumption will only take place after the calling coroutine has proceeded until its next call await. But if the thing is called from outside the coroutine context, it will immediately get executed without the awaitable or anything having to have any knowledge about our framework, about its executor, things about everything. So the only thing we need to do now is to provide access to the currently used executor, and we can use it to defer coroutine resumption. And the property of coroutine running uninterrupted will now hold. So the last thing to cover is, okay, how do we enter our asynchronous universe? We have been talking so far that every coroutine needs a parent coroutine suspended in execution, which opens up an obvious question, okay, how do you get the first coroutine running? Well, in order to do this, we have our blocking function run, which accepts an event loop. It could be Boost.Asio IO service, could be Qt's Q application, it could be something house built, whatever. And the awaitable, it would start the awaitable and drive the event loop until the awaitable completes and then return this result. We'll all propagate the exception back again. And obviously, in order to be able to interact with the event loop, it needs to be adapted by specializing this class event loop traits and telling us how to enter the event loop and how to tell it to exit. So now, as we discussed in the beginning of the talk, if you start introducing coroutines to an existing code base, chances are that asynchronous I/O scenarios are already handled in somehow, and you need, most likely through callbacks, and if you need to fit in those scenarios, it's quite likely that a piece will sit somewhere in the middle, both calling and being called from other layers, and those are probably all implemented through callbacks or promises or anything like this. And in order to be practically useful, we need this clear story of interacting with those things. One direction is calling a callback-based function from a coroutine. So here we have a begin thing which accepts a continuation callback, which will be invoked when the operation completes. And we want to suspend the coroutine until it completes. Well, the proposed decision was already being discussed. The right thing is just wrap the thing into an awaitable. This is going to cost you roughly about a dozen lines of code, which is tolerable, and also you might get to provide a clear story about the asynchronous cancellation, assuming this thing can be supported by the primitive you were trying to wrap. We also implemented this generic until callback call thing, but it was quite hard to use correctly, and I believe was never used since being implemented. So whenever we need to adapt something callback based, we should just wrap into a waitable interface and call it a day. The other direction is a little bit more interesting. Let us suppose we have this interface we're going to implement. We have this read function, which is supposed to fill in the buffer and invoke the callback when done. And we have the implementation, our nice coroutine do read, which would do this thing asynchronously. And we need to bridge these two paradigms. Well, we already discussed how to do such a thing. Get ourselves a nursery, start the thing into the nursery, which would delegate to the real implementation, then call the callback. And of course, we need to account for any errors. So a try-catch block is really non-optional here, as now we need to bridge the different paradigms, the different ways of reporting errors. The only non-trivial question here is where to get this nursery from. We already talked earlier that one way to approach this is to have this asynchronous run thing, which would open nursery, stash the pointer, suspend, and that would largely solve the problem. But that would require this thing to only be usable from the asynchronous context. So in order to create such a thing, you'll need a coroutine, which will probably be waiting for some parent coroutine. So it would require you to have a chain of asynchronous coroutine functions terminating in a run, and which is probably somewhere near main. If you can afford something like this, then fine, you have solved your problem. But what if we don't control what's up the stack? What if we implement a sort of a plugin, a shared library, or should we load into a process which doesn't know much of anything about our asynchronous framework, the coroutines and stuff? So in order to solve this problem, we added an unsafe nursery, which behaves pretty much like a regular nursery, but like it does have a public constructor and can be placed in a class just like a regular member variable. It should be well understood that unsafe nurseries exist for the sole purpose of violating instruction concurrency principles. It's kind of ironic how we put so much effort into guaranteeing that those will hold, and now we provide a way to circumvent them on purpose. So all tasks submitted to an unsafe nursery will still have a parent node, which is unsafe nursery instead. But the unsafe nursery itself doesn't have any parent, and next as a root node in an isolated another task tree. So which has a number of interesting important consequences. So one thing is, again, we don't have any clear way of error propagation. So if any task submitted to the nursery raises an unhandled exception, well, we're going back to slide 1, choosing between dropping it on the floor and terminating the whole process. And another problem, even probably more important and more difficult to solve, is that unsafe nursery does have a public destructor, which can be called at any point. And it cannot afford to leave running things behind. So it needs somehow to cancel all of them, but as we already discussed, this cancellation may require asynchrony, which cannot be simply implemented from a destructor. We will still make one attempt to cancel anything in the nursery, but if it didn't help, if anything was still running there, well, we're again stuck between choosing to allow it to leave it behind and allow it to run unsupervised, and again terminate the whole process. So it's kind of sad that we're back at slide 1 with those problems pretty much resembling all the problems we have with callbacks or detached tasks. In practice, it doesn't bring much of additional pain, as the purpose of an unsafe nursery is basically to bridge different code pieces implementing different paradigms, and those are problematic anyway. You still have to somehow catch those exceptions and map them into a problem domain-specific way of reporting those errors. So even if our safe nursery did not terminate on those uncaught exceptions, you still have to catch them and somehow report them to the upper layers by calling error back or by providing specific value to your callback function. So you have to do this anyway. And likewise, even it cannot destroy a nursery, an unsafe nursery which has background tasks in it, which cannot be cancelled synchronously. But chances are an unsafe nursery is a part of your component, and tearing down such components synchronously will still has something running in the background which cannot be dropped into the floor. It's still logic error anyway. So you still have to somehow count for those asynchronous tear down of this thing. So the only thing we have here is, yes, we have this sufficiently big type unsafe thing, which probably put some thought into when people are starting to use this. And yeah, we carefully propagate all the consequences we use in this thing. So last few words about our own experience of using the whole thing. So we have implemented an asynchronous framework around the idea I've been talking about. It's been available for us for a little over 2 years now. We employed a number of our IO-bound applications to simplify and streamline those asynchronous control flow. So whenever we take a piece and re-implement it using coroutines, well, we routinely see 40 to 50% code size reduction. So the control flow becomes much more easier to read, understand, and modify if necessary. We get much less user interference, much less hard to reason thing about object lifetime. And also value our uniform interface for cancellation and timeout. Those timeouts, they used to be so difficult to implement using callbacks, so those things were frequently overlooked, much more frequently we're comfortable with, and now we have uniform way of handling with those. To give you some ideas of how difficult it is to implement in a traditional world. So I believe operation cancellation has been added to ASIO 171, I believe, definitely 70 something. So more than a decade after ASIO itself was a thing. And of course, on the other hand, the ideas around which the framework is built is certainly novel. It requires a certain amount of training, getting used to, especially for people who get quite professional, right, in complex, intricate, entangled callback-based control flow. And of course, there is an effect of performance, as sadly, coroutine optimization is still rudimentary at best at most compilers. And of course, all this machinery we have been discussing so far does add its own fair share of performance overhead. So for measurement, we figured out that resuming a coroutine takes roughly as much CPU time as one malloc. And spawning a coroutine, like creating a new thing in a heap, is roughly equivalent to like 5 mallocs-ish. The one thing we teach people about performance is that you get the idea what your asynchronous operation, or the nature of your asynchronous operation. So if it's like, I don't know, a few nanoseconds, then probably, if you're really counting nanoseconds here, then probably coroutines is still not the best choice for you now. But if it involves at least one syscall, its overhead is going to like outweigh all those coroutine performance probably by a few orders of magnitude. So just use coroutine and benefit from a better code reliability, better code readability. So all in all, after 2 years of using coroutines now, IO-bot application with complex control flow, we can say that they are helpful indeed, and they do simplify certain use cases. So people who got used to them, do enjoy using them. So yeah, after some time using it internally, we decided to share it with the outside world. So we released it a few months ago on GitHub from, under MIT license. So if you folks are interested, if I managed to interest you with all this thing, you're welcome to check it out, play with it. It's come with support of Boost.Asio out of the box, and can be also trivially adapted to any other existing or in-house built or new event loop you might want to see and you might want to have. So yeah, that's basically all I have for you today. And yeah, if you got any questions, I believe we have like 20 minutes now left for them.
The microbench or the performance numbers you quoted all sound like they come out of microbenchmarks. Do you have like whole system experience where like you changed something to coroutines and looked at the system like writ large to see what the performance differences were?
Whenever we do such a thing again, probably chances are it's going to like to have some other bottlenecks regarding performance. Like again, if you have a system call anywhere in the stack, probably performance overhead of coroutines are going to be negligible compared to that. So in practice, we haven't seen any impact on performance whatsoever.
I'm asking in particular because I could imagine better tracking of cancellation allows your whole system to just get more efficient as you process cancellations more
yeah, I mean, in this particular case, probably we're using as a baseline a coroutine-based a callback-based approach with the cancellation still be like carefully and toilsomely implemented. So yeah, like again, it's not going to have much of any practically visible performance impact. But again, if we compare like callbacks to coroutines, especially if we account for the cancellation thing, then yeah, like the code can be probably 2x, 3x shorter. And again, of course, like you need to think what your asynchronous operation is like. So if you're doing a synchronous queue, which has less than 1 malloc per operation, then expressing the operation as a coroutine is probably going to have some considerable performance overhead. But even then, you still can express this as a state machine, as you would do before, and then advertise its like begin thing with a continuation callback as an await suspend. So it could be still used from coroutine context, but without much of any performance overhead.
You mentioned the two combiners, the all of and the any of, which cancel in case of error. The any of cancels everything but the first. And another common model is the model of polling, to wake up for the first in a loop and then wait for the next one, but handle each of the tasks when it completes somehow. So is that something that's doable in your model? Is that does that fit structured concurrency?
I'm not sure what I fully understand your requirement.
So I'm looking for something that's sort of like any of, but will not cancel the currently the still running tasks, but will just force me to wait for them after I handle the first one. Sort of.
I'm not exactly sure how you would express this in C++ thing. So once your any-of completes and resumes the awaiter, you cannot afford to run anything running in the background. This would violate starship concurrency.
Yeah.
So you probably have to employ some creativity in here. So you probably could split your thing into like more primitive things and call this any-of in the loop or something like this. But yeah, like direct select model does not fit particularly nice here.
Good, thank you. And somewhat related to that, I believe the currently proposed senders-receivers model is also a form of structured concurrency. Can you tell us a little bit about the differences between the Corral library versus what's planned for?
I'm not aware of the send-receiver thing, but I believe this should have been a talk sometime in the conference. So after I familiarize myself more, feel free to find me and we'll discuss in the deeper detail.
Thank you.
So coroutines are cooperative multitasking.
Mm-hmm.
And my understanding is that you can get more throughput with cooperative multitasking, but actually the latency would suffer. Because, I mean, your coroutine, it runs as long as it runs. The other one, even if it's ready to run, it is blocked until this coroutine says like, okay, now I'm not able to run, you can run. And this is where the latency would basically suffer. What is your experience?
We haven't seen anything like this. And again, our design implementation choices are internally single-threaded. Or like, from our practice, you could probably lose more on properly done cooperation between the threads and synchronization than you might get from having multiple things executing concurrently. And yeah, like this, our single thread approach gives you like a fine control over cancellation, over suspension points and stuff like this, and allows you to reason more easily about concurrent nature program where we program without having to do any sort of synchronization. The thing is, practically, we've seen being able to say to write like 10 gigabit, 25 gigabit links from a single thread. So I wouldn't say like we're dissatisfied with the performance. So the only thing
then it's kind of finer-grained, I would say, selection, like how many coroutines you want to run in a single thread, right? Because you cannot run like million coroutines in a single thread. Then
sure you can.
Yes, you can, but then you would end up with really like, I don't know, maybe P50 numbers being very high.
Again, we haven't seen this in practice. Again, like our recommendation so far is like, yes, spawn as many coroutines as you want to, as you need to. So again, one of the distressingly common scenario is how you can, like, imagine you have a million tasks to process, and you need to limit the concurrency of those things. You need to process somehow all of them, but you can also afford to process like 50 of them at any given time. So normally you have like 50 workers, task queue, it will dequeue the items from task and then process them. How the recommended course of action with our coroutines is spawn a million coroutines, have them acquire a semaphore with initial value of 50, and then the framework will take care of the rest. Works like a charm. So the thing is, even though with coroutines, you can spawn a million coroutines, but the overhead in synchronization is so negligibly small, you will hardly notice anything in practice. Which would not be the case if you accounted for multi-threading.
Okay. Thanks.
Yes.
Okay. You said you reduced the code size, and does that means in C++ code? In previous slide you said the code size is reduced.
Mm-hmm.
And does that mean the code means C++ code?
Yes, C++ source line.
Source line, right?
Source lines, yeah. I did not measure like the size of the resulting object.
Okay.
What happens if an exception is encountered while canceling the task?
While canceling, exiting by an exception is a case of like exiting normally. So even if you canceled and then you raise an exception, it will be treated as you complete it normally and raise an exception.
But then how does it work with something like any of, which is supposed to ignore the results of the thing that finished second?
Well, here we are into the problem of C++ not allowing you to have multiple exceptions in flight. So yeah, here's one thing, but we deliberately chose to drop exceptions on the floor. So if there's one of those already in flight, so like you have two any-ofs, so you have two awaitables, combined through any-of, one of them raised an exception, then you try to cancel the other, and it managed to complete and also raise an exception, then the second one will get dropped on the floor. Well, that's, again, there isn't any like good choices here. So you cannot like combine those exceptions to some like multi-exceptions of any sorts. It would be impractical to work with. Again, like this Python 3.0 thing has been like dealing with this for quite some time and did not succeed in providing much of any like pleasant to work with interface. So we deliberately chose not to do anything here, but reducing like two exceptions to one is probably not an ideal, but still much better than reducing one exception to 0.
Thank you.
No, if I understood correctly, when you cancel the coroutine, it will resume just to make a cleanup, but otherwise, if it doesn't need any cleanup, it will just drop and never resume the.
It will not resume in a way that the real coroutine handle associated with the coroutine will get its resume function called, and so it will get destroyed. But it might get resumed in certain cases if it's required by the awaitable it was suspended on.
Okay. So in this case, it would, if it had an exception, it wouldn't be internally to the processing of the.
Say again?
If something raises an exception during this cancellation, it would be outside of the coroutine. It would be on the structure of the promise or something like that.
I mean, if you get canceled, you don't have any opportunity to raise an exception.
Mm-hmm.
Because you don't have a piece of your code being executed at any point.
Yeah,
So in order to raise an exception, you need to somehow get on CPU.
Yes, exactly, and that's more or less what I'm trying to understand. So there's no way to raise an exception during cancellation.
I mean, there is an option. I mean, if your coroutine got requested a cancellation, but the awaitable was suspended on, managed to complete nevertheless a requested coroutine resumption, the coroutine will resume normally, but still have a pending cancellation. It will get canceled on its next co-await, but if it manages to raise an exception before that, it will be deemed as completed normally. I mean, it might not necessarily have any co-awaits after being suspended.
Mm-hmm.
So just like a regular awaitable, a coroutine may also complete normally despite being requested to cancel.
Mm-hmm.
I wonder if you try to use fibers before you ran to use coroutines from C++20, because some of the mechanisms that you describe are like you're trying to schedule coroutines, and fibers that already come with the scheduler.
I tried to use fibers in one of my previous jobs, not here at Hudson, but I'd say stackless coroutines that appear in C++20 have much less overheads. Like I said, you can't afford to have millions or tens of millions of coroutines in flight. You probably cannot afford those in fibers for the beginning. You have to allocate stack to each of those. And also, performance overhead switching from fibers to fibers also have to be much inferior, much better, much bigger than performance overhead switching between stackless coroutines. So if we're talking about real big numbers, probably stackless coroutines are a better choice.
Talk to me afterwards.
Sorry?
Talk to me afterwards.
Okay.
I'm not sure, but I think you mentioned that you deliberately chose to use type erased coroutine handles instead of knowing the promise types.
Mm-hmm.
And if I understand correctly, that's what led you to do these cancellation tricks with looking at the structure of the coroutine frame and the pointers to the resume functions, etc. In hindsight, do you think maybe I'm not sure that I described the dilemma correctly, but you think it would have been better to just use typeful coroutine handles and not type erased ones, and would it have saved you on this trickery?
I mean, in this case, you, as an author on a waitable, you'd have to choose which asynchronous framework you're going to support. And this kind of, and as an author on the waitable, I don't want to think about this. I just want to resume the coroutine handle I've been passed to. And I believe, again, the coroutines are still pretty immature still in the ecosystem. But I hope that more awaitables will continue emerging without having to know about that use concurrency framework. So dealing with type erased awaitables, you don't have to think about what concurrency framework does your client use. Actually, we tried to do the other things. I mean, we didn't implement this, but probably, as you know, Asio colon use awaitable provides you wraps an asynchronous operation to an awaitable, but this awaitable can only run within a Boost.Asio thing. So again, once as we're using our own house-built I/O multiplexer and thing, we cannot use this Asio use awaitable thing. This means Boost 1, I believe 82, which is an asynchronous MySQL client, but we cannot use it. It's useless to us because it requires Asio. So we actually put some interesting thing, and we added to our framework with that as Asio underscore awaitable, which traps this thing into another kind of awaitable, which is capable of working with type erased coroutine handles. So now we can use it both with Asio and with other things, and probably much of anything else. So we would rather see more people writing more awaitables with type erased coroutine handles, where they can interact with each other without knowing pretty much of anything about each other, which is a thing I would rather value.
So the framework you have released, it doesn't support continuation points, for example, or
What are continuation points?
like then and so on, where you could say after the coroutine is done, I want to run another one and so on.
No.
Okay.
It's not going because it's got to be a deliberate departure of such the concurrency thing. So the only thing you can do to a unit of background work is co-await on it and get resumed when it completes. That's inherently, deliberately the only way of interacting with this.
So you mentioned IOURI. Did you compare performance?
I'm afraid I cannot share numbers at the moment.
Can I talk?
Just a Boolean, higher to lower.
I mean, it allows for certain use cases and certain scenarios where we didn't even try to implement using traditional regular synchronous open read close things. So yeah, we cannot do the comparison for the lack of baseline, because it would for anyone reasonable it would obviously don't work, especially we're talking about regular files and slow devices and commands. But yes, we have adopted IOURI for our framework, and we're pretty happy using it.
A few words about the GitHub site. Are you actively developing it, or is it just a one-time dump that you put?
We're developing it as we discover new bugs and as we accommodate for more feature requests. But the thing is, again, once we released it, it's been used for a little over 2 years. So the thing is kind of in just work state. So it's not being actively developed. Well, I guess unless you people start working with it and start bombarding with the feature requests, or maybe even pull requests.
But you still use internally a version of that that's
It's synchronized with the version of GitHub.
Okay.
So what's there on GitHub is the thing we're using.
Mhm.
And probably like some portion we're not disclosing because they tied more closer to like internal IO infrastructure or something. But what we could afford could afford to release, we did.
Oh, I'm not really up to date with the coroutine, but has stackless coroutine been up there yet, or is this just something that we are discussing in the future?
I mean, they have been added to C++20.
Oh,
Stackful coroutine has been there, like it didn't require any sort
sorry,
of.
sorry, I meant the heapless.
Hmm?
Heapless?
Heapless are not there yet.
Okay.
I mean, technically the standard allows bypassing heap allocation in certain cases when the compiler can reliably prove that the spawn child coroutine will not outlive its spawner, but so far, no compiler vendors ever uses this thing. I mean, like, forget about optimizations. We're hitting like compiler errors left and right in here. So some of them get fixed, but I believe I've seen certain versions of GCC silently demoting shared pointer to be trivially movable yet not trivially destructible when used in coroutine context. So yeah, I would be more worried about about the correctness of the coroutine-based code and probably used by the compilers rather than the optimizations. But again, they got better recently, but there's still like some still unaddressed like things. Hopefully most of them, luckily most of them are ICs and spurious compiler errors. It doesn't do much of generation of invalid code anymore.
So the nursery type is not copyable and not movable, and the unsafe nursery is movable, but
it's not movable, it's not copyable, but at the very least it's constructible.
Yeah.
Whereas regular nursery isn't even constructible through any regular means other than this with nursery macro.
You mentioned that you created a proxy for the presumer based on non-standard things that you saw that all the compilers are doing right now?
Yes.
That they agreed somehow. What is that agreement? Is this part of the Itanium ABI, or is just informal agreements? How did you?
As far as I know, they didn't sign anything in blood. So the thing is the first, I see it was kind of an informal agreement, kind of de facto standard. Mm-hmm. I mean, whoever did the first came up with the idea of a structure of a coroutine frame, and the others just started copying things from the implementation of their own in order to probably let's think about things, and also in order to ensure this binary compatibility. Of course, ABI is never part of the standard and never going to be because it's kind of a different thing. Mm-hmm. Standard never covers any sort of ABI, but that was a de facto thing. And Microsoft folks were actually kind enough to make a breaking change to their own compiler in order to bring their compiler to compatibility with GCC and Clang. Kudos to them. So I'd assume no one of those three will deliberately break this thing.
I had a question,
Mm-hmm.
kind of specific question about one of your slides, the one with the bridge into it using a nursery to get back to a callback.
Mm-hmm.
What happens if the co-await was canceled? Right.
This?
Yeah. What happens if the co-await if the do-read co-await ends up canceled?
You cannot cancel it from here because the only thing that cancels is any of null of, which are not there in flight anywhere, or otherwise you can do nursery.cancel, but the nursery is your thing and it's in your capacity not to call cancel here. Cool. And if you choose to call to do the cancellation, then yes, of course you could do this, or you could wrap the whole thing to any of null of if you wanted this thing to be cancelable from external, but then you'd have to do the bridging.
Okay, thanks.
Okay.